Okay, so we've talked now about projection, we've talked now about cross product. Let's go back and do some actual 2 concrete examples that we can take from the book. So the first example is the idea, we're going to build on the idea if 2 vectors are orthogonal, then n, so let's consider n is perpendicular to a vector r minus some r naught. Then n dot r minus r naught equals 0. And the trick to the few homework problems based on this section that are based on geometry is usually to recognize, given the description, which vectors do I need to be orthogonal and which vectors do I need to be parallel. Because cross product and dot products will tell you when things are parallel, it'll tell you when things are orthogonal, and cross product will make things that are orthogonal if you need to make something orthogonal. So one thing you might want to do is if n is a vector, you might want the plane perpendicular to n. That makes n the normal vector to the plane. And this is actually an important idea, because if I think about a plane, the orientation of the plane is really only uniquely defined by its normal vector in a sense. That's the easiest one to uniquely define it, right? Any vector in the plane is kind of degenerate, right? It doesn't quite tell me where the plane is yet. But that normal vector really does uniquely define the plane for me. So it's an important vector to be able to find, or to find planes perpendicular to it. So if I have n equals ai hat plus bj hat plus ck hat, how might I find an equation for the plane that's perpendicular to that? So this is my normal vector. How would I find an equation for the plane perpendicular to that? So these are constants, right? This is some arbitrary vector with scalar constants a, b, c. I want an equation in x, y, and z. Right? So, chat on this for a second or two. What mathematical operation do I do to find the equation, an equation for the plane in terms of x, y, and z? Wait 1 second. Just chat with someone, think about it. So what mathematical operation do I want to do? What do you think?
Dot product.
With what?
A perpendicular vector, so that's r minus r theta. And
What?
you do the dot product and find vectors that are equal to 0.
Exactly. So we actually get to do the dot product with sort of any arbitrary vector x, y, z. We'll be a little more general. We'll literally do what I did up above. If r minus r0 has the components x minus x0, y minus y0, and z minus z0. Because the vector n, I haven't defined an origin for my plane, right? I can get an arbitrary set of parallel planes perpendicular to n. There's an infinite number of planes perpendicular to n. So by picking my n and a point, I'll get a unique plane. So I had to add a little extra piece, but now if I do that dot product, so if I do n dot r minus r naught, I will get and then if I set it equal to 0, by definition, every vector x, y, well, every vector x, y, z, x minus x, every one of these vectors, I'll spit it out eventually, is perpendicular to that, so it's all the points in the plane perpendicular to it that also goes to the point z naught, y naught, x naught. Now, we can rearrange this in what we call standard form. And we see that the constant on the other side is just a x naught plus b y naught plus c z naught. Now, let me ask you this. So that's one way to get a plane out. Now suppose instead of a normal, a line, suppose I just gave you 3 points. I'll give you specific ones. How might you go about constructing an equation of a plane that goes through those 3 points? Well, we have to be a little more careful, right? These are 3 different points. What's my normal vector?
Well, if you start from the origin, you have 0, 0, 0. So then you can have a vector going to 1, 2, 5, and then a vector going to 2, negative 1, 0. And if you take the cross product, you get the normal vector, right?
So I could be building it up from a cross product to get the normal vector to go do this. Now, what might be a shortcut?
Find a vector that connects, any 2 vectors that connect to those points, and then you do the cross product to find an orthogonal.
Right, so that's sort of what he was saying. There's kind of a short step going back to something we know about cross products. I can cheat a little bit and create the following 4x4 matrix. And then take the determinant of this and then set it equal to 0. And that kind of that builds in all those cross product ideas that you have mentioned. Basically it says, right, the only way, how do I make determinant 0? First of all, I need to make it 4x4. So again, this is picking, sort of, there's, setting up, the 1 is kind of arbitrary and useful. I need a 4x4, the determinant is not defined. But what does it do when the determinant is 0? What have I just said then about x, y, and z? In terms of linear independence or dependence. It's now dependent on the other 3 vectors, which means it's in their plane. Right? So any x, y, z for which this determinant is 0 is by definition in the plane of these vectors. And so it's a shortcut way of doing this. Any questions on that? In class today, we had an example problem where we were finding the equation of a plane through 3 points. And we made the matrix x, y, z 1. We used our points. We added 1s in the final column. And we said the determinant of that is 0 will give us the equation of the plane. And the question really is why. That was asked in class, and particularly why putting the 1s here. I used a rather abstract explanation in the lecture, but it's worth kind of doing this more carefully. So let's do it in the general case where we have points P1, P2, and P3. They are vectors relative to the origin because we gave them in component form. But in terms of being in the plane, the vectors that are in the plane are vectors that are the differences between pairs of these points. So for instance, the vector P1 minus P2 is in the plane, and so is the vector P1 minus P3. Now, that means if we want to find the normal, we can just take the cross product of these 2 vectors. And then if we want to find an equation for the line, we can do what we've done in the past, is set the dot product of r minus some point in the plane, dotted into the normal, equal to 0. That is an equation for the plane. And if we work this out, we would find r minus p1 dotted into p1 minus p2 cross p1 minus p3. Now, because we're using dots and cross products, a lot of things cancel out. P1 cross P1 itself is 0. So we have a minus P1 cross P3. We have a minus P2 cross P1 and a plus P2 cross P3. Now, when we do the dot product, R is going to be okay with all of those, but P1 is only going to survive when you do P1 dot P2 cross P3, because P1 is by definition orthogonal to those two terms. So this dot product results in 4 terms. There's a minus R dot P1 cross P3. There's a plus R P1 cross P2. There's a plus R P2 cross P3. And there's a minus P1 dot P2 cross P3. And this whole thing is 0. Now, what is the determinant that we set up? Well, what we set up is basically R with a 1, so that's as a vector, so this is 4 numbers across, P1 with the 1, P2 with the 1, and P3 with the 1. And then that determinant was equal to 0. Now here's the reason. We could pick any numbers that are the same, as I said, but for simplicity, we pick the 1s because it will immediately show the connection between this determinant and this expression. How do I do a determinant? Well, I can use the columns. I can take this element and the determinant of these 3 vectors. Well, we saw the determinant of a 3 by 3 matrix is just the dot product with the cross product. So this, by definition, is our P1 dotted in to P2 cross P3. Now notice there's a minus sign, but what we're going to find is there's a negative sign in all of these expressions just because of the way I picked my vectors, and so they will all cancel out. Because now I get this with a minus sign because I'm alternating, so I get minus, and now I get R dotted into P2 cross P3. Well, notice in this expression that term has the positive sign, so like I said, it's a negative one, and if I follow through, I will then get plus R dotted into P1 cross P3, and finally minus R dotted into P1 cross P2, and this determinant is being set equal to 0, so that's the determinant equal to 0. This is working out the long way, and this shows why I picked the 1s. The 1s are just convenient to make my triple products of dot and cross products work out and not have any other factor. Because I'm setting it equal to 0, I can obviously put any set of equal terms there.